2001, question 7a, statics. And in these questions there's fixed steps that we go through every time. And the first step is to draw a force diagram of your system. And in this case, the system, we got to try and visualize this. The system is a rounded peg here with two rods jointed. They're fused together here at this corner, and the rods are balancing. The rod system is balancing on the peg. So what the peg is fixed, and these rods, this rod system is free to move. So that means we're going to look at the forces on the system BCD. So let's draw that first of all. And here's the peg. So a nice big diagram won't go astray because you want to put in lots of forces. You want to make it as clear as possible for yourself and for the examiner. So let's just try and get a tangent to this peg here. So that's your first rod. And the second rod is here. And the second rod goes about that far. And I want to really emphasize that these rods are the system. So what I'm going to do is maybe highlight them in a different color for the moment. So I'm going to highlight the system. Let's see, maybe in red. So let's highlight the system in red. Here and here. So what I've highlighted in this diagram is the parts that are free to move. And this goes for any statics question. The system is the parts that are free to move. They're free to move, but they don't actually move in the question. It's always on the point of moving. And this makes it easy now to identify the forces that we're interested in once we've identified the system. So let's choose a different color, and we are now going to look at the forces that will be acting on that red system. And clearly there must be some kind of a reaction force pushing from the peg out here. So we'll call that R. In blue, and we call it R. And similarly there's a force here at the top pushing out. There's another reaction force, and we're going to call this one, we call it S. Different reaction force, we call it S. Other forces involved in this question. Let's go back and read for a minute. The rods each have a weight W. So the weight is another key force that we have to include. And weight always acts through the center. Now the center is going to be a bit further out someplace. So let's say it's maybe here. So there's a weight of that top rod, of that horizontal rod. It's going to be a weight W through the center, wherever that center is. And also the rod, the vertical rod, the center of that rod is also going to be a force W. So that's a bit harder to show, but it's going to be through the center, which may be here someplace. So there it is. There's a force W through the center point of the rod. That we call that W also. And lastly, there is friction. So it's on the point of slipping, and it's a rough circular peg, so quite clearly there's going to be friction. And the coefficient of friction is the same for both rods, it's mu. So now we've put in that also. And again, visualize is the key. Which way would the rod slip if it was going to move? It would actually tilt over this way. I mean, this bit would fall in, and this bit would tilt up. So if it's going to fall down, the friction must be pulling upwards. There's a friction force here, mu r. just label that UR. And also, as we said, at this point here, it would slip outwards like so. So the friction must be pulling it back in. So there must be a friction force pulling in like this. And that friction force is μs. So that completes the first step of our question, and that step, the important point here is that step is the same for all statics questions. Steps number 1, you always draw a force diagram. For the system. And the system is the 2 rods. Step 2 is also always the same, and step 2 is draw another diagram, but this time just with lengths only. And the length diagram we'll actually maybe do it just below. So briefly, let's just draw the peg again. This time we're not too worried about colours as such, we just want to go back to lengths only. So we'll just draw the rods again. And this diagram is, the reason for the second diagram is to avoid clutter really. You could have done this in the first diagram, but it makes it very cluttered if you put forces and lengths on the same diagram. There's no other reason for this diagram. So it doesn't have to be too accurate, just once which it clearly shows the lengths that are involved here. And when we're showing lengths, I suppose the key point of the whole thing is obviously the centre of a circle. And we'll put in our radius, which goes to here and to here, because those 2 rods are like tangents, therefore the radius is perpendicular. And let's get some lengths from the question. We're told that the length of the rods, each rod is length 4L. So maybe if we just mark the halfway point here, that means it's 2L and 2L. And we've got to be careful, of course, not to mix up the length of the rod with the dimensions of the circle. That's 2L to the halfway point of the rod, and 2L there also. And it's going to be the same for the halfway point of the rod, which is going to be below center, because again we're told in the question, we're told this information in the question, we're told that the radius is less than 2L, which is half length of the circle. So we've got 2L and 2L again. And the radius of the circle, as we just said there, is actually A. And that's the length diagram done. So that's our first 2 steps. And next step, again always the same, is our 3 conditions for equilibrium. If this object is in equilibrium. And equilibrium means 3 things. Number 1, the force is up equals the force is down. Number 2, the force is left equals the force is right. And number 3, the sum of moments is 0. And we don't always use all of those 3 conditions in a question. Sometimes we can go straight to number 3, for example, but it will always be